Hello, and thank you for stopping by our poster. My name is Julie Younes. I'm a PhD student at the University of Toronto in civil engineering with a geomechanics emphasis. Today, I would like to present the effect of H2 on salt caverns during fast cycling injection production, laboratory characterization, and storage integrity workflow. To reduce the consumption of fossil fuels along with greenhouse gas emissions and prepare for sustainable energy supply in the future, renewable energies such as wind and solar are gaining attention around the world. However, these energy sources are dependent on atmospheric conditions, resulting in energy excess or deficit as seen in this first figure. Because of that, hydrogen can be used as an alternative, stored and used later when the demand arises. Underground hydrogen storage, or UHS, in salt caverns proved suitability across 4 projects around the world. However, these caverns are operated at low cyclic frequency compared to higher expected frequencies in H2 from renewables to meet the peak load demands, which can be daily or hourly, like the example for Alberta in 2050 shown here. When hydrogen is stored in salt caverns, the interior pressure and temperature of the cavern change cyclically. The second figure illustrates the potential mechanical challenges involved with UHS in salt caverns. Thermomechanical stress conditions have a major effect on the properties and strengths of salt rock, inducing tensile stresses as well as creep. The possibility of hydrogen permeation is still a concern, specifically when inclusions and interlayers exist within the salt formation. Undesired outcomes from operations include loss of storage volume, induced seismicity, fluid leakage, collapse, and failure of the cavern. Therefore, the cavern stability must be guaranteed during H2 fast cycling. Next, we present an experimental workflow in which the different processes involved in UHS are covered, involving 3 stages. The salt rock specimens are first prepared and cored using a CNC milling tool to avoid damage to the samples. X-ray diffraction (XRD), scanning electron microscopy (SEM), and X-ray spectroscopy are used to provide the mineralogy, grain structure, and existing fractures within the samples. The prepared samples are then divided into 2 sets. One of these sets will be exposed to hydrogen inside of an autoclave at in situ conditions. And in stage 2, all samples will be tested under static and cyclic conditions, in which the cyclic frequency will vary from slower to faster frequency, all while adopting a digital image correlation system to monitor the spatial variation of strain over time. Cyclic loading stresses will include mechanical, hydraulic, and thermal loadings, and fracturing fluids in hydraulic fracturing tests will include brine as well as hydrogen gas. And in stage 3, changes induced from hydrogen rock interaction will be detected from XRD, SEM, and the resulting fracture morphology will be evaluated under X-ray spectroscopy. Experiments show that cyclic frequency affects the strain of salt rock, decreasing nonlinearly with increasing frequency as shown in the first figure in the anticipated outcome section. However, thermal cyclicity and its effect on the mechanical behavior is still not investigated. Moreover, hydrogen exposure experiment on sandstone in the second figure within this section has shown a porosity and permeability change, thus affecting the hydraulic behavior of the rock due to the solution of anhydrite, which is a common inclusion found in salt rock. An example for that is shown in the third figure in this section. Such chemical interaction is yet to be examined on salt rocks, as they are often considered inert. The suggested workflow includes performing coupled thermochemo hydromechanical cyclic experiments to address the integrity of caverns under operating conditions. Thank you.